This kind of question will take you a while in multiple choice section if you're doing AQA. However, it's definitely worth doing because it could be a 2 or 3 mark question sort of elsewhere in the paper. So we've got particle of mass m, kinetic energy E. What is the de Broglie wavelength of this particle? So let's start off with our equation sheet. De Broglie wavelength is obviously h over mv. Now if we look at what else is in the expressions we're asked to give, we should know kinetic energy is half mv squared. Now we could rearrange this in a few different ways, but if you look at all the options, they've all got E and they've all got M in them. They do not have velocity. So our first step is basically to kind of cancel out velocity from these two equations. So what I would do to do that is to rearrange this whole equation for velocity. So if I pull the 2 up to here and then divide by M, and then for that equals the velocity squared, so therefore to square root it would equal V. Next, what I can do is substitute this into our equation up here. So I've now got de Broglie wavelength equals h over m, and instead of v, I'm going to do this big square root 2 of the kinetic energy divided by m. Now, sometimes people get to here and they might get a bit stuck because it seems like, oh, we've got sort of square root of m and m outside the square root. What I would do is all these options have everything inside the square root, so you've got to get this m back into the square root. So what I would do for that is then to say, well, if I pulled it out, if I could put it back in, it would just become a regular m, but it would have to be squared because I'm putting it back inside the square root. So everything else stays as it is, but now I've got an extra m squared inside the square root, and it actually means I can simplify things down because I've got now an m squared up top here, and I've got m on the bottom, meaning it sort of cancels quite nicely to give h over to root 2e, I just realised it's e rather than ek in the question, times by m, which if you look at the options here, that is option D is the correct answer here. Over to a question about electron transitions, and this one has no numbers, it's all done to scale though, which gives us a clue on how to solve this. So we've got a transition from E4 to E2 is going to emit green light, which transition could cause the emission of red light. Now we should know colours of the spectrum, we've got red at one end, we've got violet at the other, green is somewhere in the middle. So comparing green to red, this has a higher wavelength and a lower frequency. So depending which way you want to look at it, I'd choose frequency personally. We've got to find a transition that has a lower frequency, and due to E equals HF, that means it has a lower energy change. So the only one that's out of these options here, you can go through one by one. E2 to E1 is bigger. It does say it's to scale, so it's a bit bigger. E3 to E2 is smaller, and the rest of them are bigger as well. So the one we'd actually look for here as the correct answer is the one that's smaller than the original change, that gives a lower frequency, which is going to be our red light. So it's the answer to this one is E3 to E2. Another question about de Broglie wavelength here. Again, we've not got many numbers, but we've got a positron travelling at 5% the speed of light. So the de Broglie wavelength is given by h Planck's constant divided by mass times by velocity. So Planck's constant, we should know 6.63 times 10 to the minus 34. The mass of a positron, we need to know it's an antiparticle of an electron that equals the same mass as the mass of an electron. So that's given by 9.11 times 10 to the power minus 31. Now 5% of the speed of light, you could do the calculation first, but you don't have to. 5%, we could just write it in here. So 0.05 times by 3 times 10 to the 8. You stick that all into your calculator to get a final answer, and it equals 4.9 times 10 to the minus 11, which is option D in our question. Next, we've got a couple of questions about photoelectric effect. So for this question, it says monochromatic light with a certain energy 4.1 times 10 to the minus 19 is incident on a metal surface. The speed of the electrons that get emitted is 4.2 times 10 to the 5. So what we know about photoelectric effect is that if I've got photons coming in, their energy is given by HF. It'll cause an electron to be emitted from the surface with a certain kinetic energy. So the overall equation for this is HF, the initial energy of the photon, equals the work function plus any kinetic energy left over. So the work function of metal is what we're trying to find here, and we actually don't need HF because we already have the instant energy. So this is just going to be the energy it comes in at, which is 4.1 times 10 to the minus 19 joules. So we can rearrange this equation, and we know what kinetic energy is as well, because we know kinetic energy equals half mv squared. We know they're electrons, and we know the speed they're travelling at. So the mass of an electron is 9.11 times 10 to the minus 31, and the speed they're travelling at is, given in the question, 4.2 times 10 to the 5, making sure to square it. So this gives us the value of kinetic energy of the electrons. If you put those numbers into the calculator, it's 8.035 times by 10 to the minus 20. And to get our final work function, let's rearrange our equation. So work function equals the initial energy, so 4.1 times 10 to the minus 19, minus the kinetic energy of our photoelectrons, which, if I can write properly, is going to be equal to roughly 3.3 times 10 to the minus 19, meaning it's option B in this question. This question is about the graphs plotted when you vary the frequency of incident radiation demonstrating the photoelectric effect, and you measure the kinetic energy of the photoelectrons that are emitted. We've got a metal surface photoelectric effect. This is the initial graph. So it says P is the intercept on the x-axis, Q is the intercept on the EK axis, which graph shows the variation for a metal with a greater work function. So greater work function, if we remember, the work function is the minimum energy, can't spell minimum energy required for photoelectrons to be emitted, for basically the photoelectric effect to occur. So if that's the minimum energy, if you increase that, it is going to change our graph. Now we need to know a couple of features of this graph, and one of them I would definitely say to memorize is that if you were to rearrange the whole photoelectric effect equation for this part here, is that the gradient of this graph is going to be equal to Planck's constant. So that can't change. From this gradient here, it can't be the ones that are steeper or shallower. It has to have the same gradient. What that will do then is if we look at what the intercepts represent, so it's going to be one of these two here, A or C. If we look at what the intercepts represent, this one here, when there's no kinetic energy, this one here is the work function. So work function is when basically there's no kinetic energy, so essentially HF is equal to the work function. If we were looking at this one down here, kinetic energy, this would basically, if you trace back, this would be what would happen, the threshold frequency. Have a look at this graph here. Q is what would be the work function. So that's what's going to happen when there's basically zero frequency, basically the minimum energy that's required for the electrons to be emitted. At P, the x-intercept on the x-axis, that's going to be what's known as the threshold frequency, or F0. So the frequency at which this just occurs when there's no kinetic energy for these photoelectrons. Now both of these change when you've got a greater work function. So it's going to be part C. It gets a higher threshold frequency and it gets a bigger work function. So the answer is going to be option C in this question. Okay, this question here is a fairly standard question all about energy transitions in an atom. We've got ground state, we've got energy levels. It says transition from X to the ground state produces a photon of wavelength 147 nanometers. And then we've got the other one from transition from Y to the ground state. I can't draw that properly. There you go. Y to the ground state is going to emit a photon with 160. So the question says, what's the energy difference between X and Y? So energy difference, the general equation is this. So energy difference between atoms is HF, or you could say it's equal to HC over lambda. So we know the difference in energy is what we're looking for. Planck's constant we know, so 6.63 times 10 to the minus 34. Speed of light we know, 10 to the 8, and divided by our wavelength. Now we've got to use the change in wavelength here, which is going to be a difference between there and there, which is 13 nanometers. So 13 times 10 to the power minus 9. If we put those into our equation, and then we'll come up with an answer which should round to 1.1 times 10 to the power minus 19 joules. Questions like this one here, where you've got ratios and it's part of a multiple choice set of questions, can really confuse people in A-level exams. However, trust me, it's really not as hard as it seems. De Broglie wavelength of an electron versus that of a proton. So the equation for de Broglie wavelength is h over m times by the velocity. They have the same velocity, and Planck's constant is a constant. So we can effectively ignore these here and just say that the de Broglie wavelength is inversely proportional to the mass. So essentially what we're going to say then is the de Broglie wavelength of the electron over the proton is going to be equal to, because they're inversely proportional, the ratio of the mass of the proton over the mass of the electron. So you can either put these values in, or you can just look, and we should know even from GCSE, the mass of a proton is about 2,000 times bigger than the mass of an electron, so it is going to be option D, because the answer will round if you divide those two masses together to around about 1,800. Next question we've got is all about work function and the photoelectric effect. So monochromatic light with energy of this is incident on a metal surface. The work function is 2.4 electron volts. What's the maximum speed? So we can use the photoelectric effect equation, and we are going to have to make sure to convert this in electron volts into joules to be able to use it. So HF we don't need to know because we've already got the energy from the photon, so we can just write that in straight away, 4.2 times 10 to the minus 19. Work function, we need to convert this into joules. So to go from electron volts to joules, we go up in the alphabet, so we times by 1.6 times 10 to the minus 19 to find that into joules first of all. So that is 3.84 times 10 to the minus 19. So we put that in place of our work function term down here. And then add that to the kinetic energy. Now, kinetic energy, we're trying to find the speed. So kinetic energy of electrons is equal to half mv squared. Now, mass of an electron we have given to us on our data sheet, 9.11 times 10 to the minus 31 kilograms. So let's solve then for v. So 4.2 times 10 to the minus 19 minus this term here, 3.84 times 10 to the minus 19, and that equals half mv squared. So to get half onto this side, I'm going to times the whole thing by 2, and I'm also going to divide it by m. So I'm just going to put this here just to save a bit of time, and that will all equal v, and to square root it at the end will give us v instead of v squared. So if I put all those numbers into my equation, we should come up with answer C for the speed of our electrons, which is 2.8 times 10 to the 5 meters per second.